viewers. So today's topic is network science for sustainable applications with case studies. So in this lecture we will be exploring different aspects and the applicability of network science technology, tools and different platforms that are available for the sustainable applications. And for this we will be exploring with some case studies with real world applications, real world instances and all. So in the title itself you must have seen that there are two new phrases that is coming up. Okay. So the first one is network science and the second one is sustainable applications. So to understand what are sustainable applications, let's dive into what are the sustainable goals. So these goals are established by UN, the United Nations, in 2015. So these are the different challenges confronted by the society on the domains of social arenas, or you can say the economic fronts, environmental challenges and all. So in this lecture we will be seeing that how with the help of network science and AI we can achieve these goals, that is we can develop some strategies or problem solving approaches for these kind of sustainable development goals. Now to understand further we need to know what are the networks before we know that what is network science. So network is basically the symbolic representation of the pairwise relations of the real world objects. Now what is symbolic representation? It means that you may have a term and there could be a text based representation or a numeric description or something like that, but when we have the visualizations it involves certain notations and symbols. So with the symbols it becomes very easy for the the user to understand the significance of the underlying structure. So that's why we have this symbolic representation of the objects that are connected to each other through some kind of pairwise relations. Now these relations could be of different forms. It could be the connectivity, it could be interactivity and many more. So let's understand one by one. Connectivity is the simple connection that two persons are connected. For example, in Facebook, friendship is a kind of connection. So that becomes the connectivity aspect of a pairwise relation. Why pairwise? Because two objects are connected. Okay. Next is interactivity. In some of the social network or the social physical world networks, we have some interactions in form of, you can say, the sharing of ideas or communication of certain concepts regarding some trends that are going on. Okay, so that becomes the interactivity. Similar properties are when two objects are sharing same kind of structure or same kind of some behavioral aspects. Belongingness is something like a hierarchical structure. So when you have a hierarchy, for example, if the students, we see from the perspective of the students, there could be UG students, the undergraduate students, the postgraduate students, they are connected to certain university and university may be following some pattern affiliated to central universities, central bodies and all. Okay. So this forms a kind of belongingness of a particular individual entity with the higher order. And the objects with which these entire relation and the interconnected structure is being formed, these are nothing but the real world profiles. So if we are taking the example of the social networks, it means that the people itself will be the objects. If we are taking up the transportation network, then the places that are connected with each other through railways or airways, etc., then these places will become the objects. Now if one object is connected to another and the other object is not connected back to the first one, then it becomes a asymmetric structure. If both ways there is a connection, that is the relation is a bidirectional, then a symmetric structure of the network evolves. Now this is all about how the nodes and the links are there that connects a particular kind of interconnected structure. But what are this relation between the networks and the graphs? These are very synonymous terms, but in a very core level, if we want to understand, graphs are the connected structures that we often take up when we are discussing about the modeling aspects. Okay, we have created some protocols, we have created some analytical techniques, or you can say some communication algorithms or interaction algorithms, and we want to test it before applying it to the real world. Okay, so then it becomes the graph for the modeling aspect. Once the modeling is done and our technique that we have proposed or built is working properly, then we apply it to the real world scenario and then it becomes networks. So when we are say for example analyzing the social interactions of people in the online communities, let's say for example, then those becomes the social graphs that we are analyzing with respect to certain trends or keywords or maybe some profiles, etc. But in actual world, these social graphs, when it comes on the public domain, it becomes the social networks, and we have Twitter, Facebook, Instagram and many more. Okay. So this is the very basic primary difference between networks and graphs. But for this lecture, you can use these two terms synonymously. Okay. Now next is what these networks and graphs they represent, why we study these network science technology for understanding the applications and building some sustainable solutions for these applications. So the thing is, why networks in the first place? Now the networks present the interconnected components in a very easy to comprehend manner. Also, it represents all forms of information simply with the help of the nodes, that is the profiles or the objects, and the edges connecting between them, that is the links. So this facilitates the analysis of the connectivity in form of the flow of information and the topology of the network. So there are different applications of this. It could help for identifying the pattern of the spread of information in the network. What else we can do with network science? We can also find the shortest paths that are prevalent in a network. What are the optimal work schedules when it comes to the production networks? When an item or a, say for example, a product like car is being manufactured, then first we get the parts, then we assemble it, and then we go for the delivery networks. So there are certain work schedules. So it becomes very important to optimize those schedules to have minimum cost incurred but best results involved. Then we can find out the influential nodes that are in the network using different kind of centrality techniques. We can also perform cost benefit analysis to see whether a link or a interaction that is being presently involved with a pair of node, is it beneficial for in the future also that the particular interaction stays intact. Maybe because the cost of that the maintenance of that link or the association is higher, so there may be a fair chance that those two nodes may not prefer to stay connected. So likewise, we have different kinds of link prediction algorithm that stays above this cost benefit analysis. If the cost benefit utility score is more, then the link will stay in the future, otherwise it may vanish or it may drop. So there are different software tools and techniques, visualization platforms to visualize, to see the random behavior, or you can say the power law behavior, sometimes whatever the real world is impacting on the communication pattern, the behavior of the users or the online people who are connected to the social networks, or the people who are connected to the physical world, like the transportation network, communication network, and also the classroom network. So for all these analysis, we need the understanding of the networks and therefore the network science. Before we go more into network science, let's understand what are the different types of networks available. So let me help you understand some of the graph types, and with each graph type how the nodes and edges are to be described, and some of the real world instances. So technological network. For a technological network, there could be power stations and places that are connected with each other. So they become the nodes with which these things are connected. Maybe sometimes the power stations, they are connected with wires. So the wires will become the edges or the links. If the places are there, then they may be connected through roadways or railways, airways, etc. And what kind of real world instances are there? The power grid, the transportation network. So these becomes the examples of the technological network. Similarly, you have communication network, and when you are communicating, with what devices you are communicating. If it is a social physical world network, then it is us, the people, who are directly communicating, like I am communicating with you, right? So then the people becomes the nodes. But if there are certain devices that through laptops, through phones, or mobile devices, people are communicating, then the communication devices, they become nodes, and the communication link or the coverage of the wireless network becomes the edges. And hence we have the telephone networks, internetworks, and all those things that are in the real world, they become the examples for communication network. Similarly, you have endorsement network, and you can try to understand what kind of nodes and edges could be there in case of the endorsement networks. Similarly, we have the information network, we have metabolic network, ecological network, and computer networks. In the computer networks also, again similar to the communication network, you can see the computers, the servers, these electronic equipments, they become the nodes, and the topology, the coverage, they become the edges. Okay. These days people are very much into social network analysis. In social networks, you can see that there are different instances, Instagram, Twitter, etc. And the friendship or the likes or following follower behavior, all these, they form the edges. Similarly, the commercial networks, when it comes to logistics, the production, the flow line, any dependency, if it's there in the process, then they become the edges, and the product itself, the parts itself, and if it's a market dependency network, then the market itself will become the nodes. And then you have few instances like the manufacturing network, production graphs, and many more. Now, seeing the network types, we can also understand that there are different structures, and with respect to each of the structure of the network, there is a specific kind of structural importance. So if we see the road networks, we can see that there are patterns of blocks, because these are the blocks where the people are residing in the cities or towns, and there may be some residential apartments in between. So we have blocks, block kind of network. So interactions in form of the interconnections of where the roads are meeting each other, you can see them with thickening of lines. So if it's a highway, it's a more thickened line, and then there could be some service lanes, there could be within the cities there could be some lanes. So likewise you have the road network. In the rail network, what happens, more of a chain kind of network you can see, that is spanning all across the space. Okay. So these are again as per the rail connectivity, how the rail lines are being plotted. Then you have the production or the logistic network. So as I was saying, that there is a kind of sequence along with the connectivity. So in other networks you can see the connectivity. In the production network or the logistics, you can see the connectivity as well as the sequence. So there has to be a directivity associated with the connections. The stages that are connected with each other, or the stages that need to be done prior to other stages, has to be in the phase 1, and then phase 2 would be the one that are dependent on the earlier phase likewise. Then you have power grids. So here you can see that there are some kind of you can say nodes that are more powerful, or maybe you can say more power repositories are there, and then it is gradually going towards the small communication units like houses and small scale industries and all. So it's more kind of a rooted tree structure. In the graph you can see a very interesting theorem, you can say, that's coming up, is the average path length and its impact on the number of increasing connections. So as the number of connections are increasing, what is happening to the interconnections, the nodes? So now the nodes that are connected to each other, any two nodes, any pair of nodes if you take up, you will see that the path length, or you can say the average path length, is gradually decreasing. So if you are taking the first graph, graph A, in that you can see it's just a chain graph. So if a pair of node, that is the in the head and the tail node, if we are taking, so you can see there is a huge path length between the first and the last node, right? So it means that the average path length for graph A is more for a particular kind of pair of network. Okay. So these networked nodes, what will happen to these? When there are information available to a node at the extreme of the network, then it will take more time for that information to reach to the other extreme of the network structure. As we go further, you can see the graph D, where the connection is in form of mesh. So as the connection becomes dense and the nodes remains the same, so naturally what is happening, we are moving towards more of fully connected network. So when the network becomes connected with more number of links, then the average path length decreases. So we take up any pair of node and we'll see that they are connected through very small number of links, and if it is a fully connected network, then it is connected with a direct link. Okay. Now let's understand the different aspects of network science. Now network science is a wide umbrella. It is spanning through several cross-disciplinary branches. Like we need to know mathematics, we need to know graph theory, computer science, and many more aspects that involves not only just the computation, programming, but also the context part. So in this diagram you can see that it's a co-occurrence network that is visually trying to capture the research concepts in a Turkish university. So in this what happens, there are many students in this particular university, and they are say for example doing research in different vivid areas. So this data set will have the details of the students and whatever the keywords or the concepts or the technology they are working in. But the thing is that a student or a researcher will not work on a particular topic as a standalone. Okay, so you can see in this graph that neural network is a keyword that is being highlighted, and you can see that from the neural network there are edges or there are links that are associated with other keywords also. It means that the students who are working with neural network may also be interested for the image processing, for other machine learning tools. So that way these nodes are connected to each other. And naturally, the topic that is most prevalent, most in trend, you can see them on a more highlighted form. That is, the node size has been shown in a large manner. Okay. So these are the different ways that the visualization can be done to capture attention of the learners and to make it easily comprehensible. Now next is the wide range of methods and metrics that are available to understand network science. So these are mostly surrounded around the data centric analysis or the modeling, or if the real world applications are there, we can have the real world data and do our experimentation. And also we can use technology like generative AI to generate some synthetic data that is generated in a manner so that their distribution remains same with respect to the original data. And this helps to address our scarcity of data problem. So these are different things that we can do with data and the network science. Network science has emerged as a significant way of demonstrating the underlying connectivity of the large scale graphs. Now, what are these large scale graphs? We know the graphs, right? But there is this tendency of the graphs. They are always growing. Growing in the sense that maybe the number of nodes are increasing, or that the number of nodes remains same, that is the participating nodes or the participating entities, they are same, but their interconnections are increasing. So there is a tendency of growing of the graphs. So when we are studying the network properties or modeling the network properties onto a graph, then there are some concepts like random graphs, where the nodes are connected to each other just randomly. Preferential graphs are the ones where the connections are based on the preference of a particular pair of nodes that with whom they want to get connected. And then comes the growing networks, in which there could be a hybridization of random and the preferential connections. So most of the real world networks, they are growing, be it the transportation network, where the reachability is being constantly increasing. So effort is there to increasingly connect those places that are far away. Okay, so it means that more number of nodes are getting into the transportation graph. Also, the alternate routes are being constructed. So these routes are what? They are the links. So the graph in the real world tends to grow. And these kind of networks could be from the social domain, from the biological domain, knowledge domain, and many more technology domain. Also, we can explore the properties of the real world systems that exhibits these kind of complex structures, spatial dynamics, temporal dynamics, and many more, which we will see in the next lecture. So thank you for listening. Thank you.